Hello and welcome to the module Advanced Software Testing and Analysis. We stay in the bigger area Advanced Testing, and today in this video we will talk about combinatorial testing. I assume that you've read both reading materials available in Ilias, give a very brief introduction and then only ask questions about the reading material. Our general idea of combinatorial testing is something that I like to think about in terms of cars, because they are for me one of the products that have the most possible combinations. You need these very complicated software systems there where you can configure your configurations for a car that you want to buy. And all these possibilities are sometimes called factors. And then we want to understand what factor combinations are possible, and these combinations, certain combinations, we also call configurations. And the problem is that they have become very quickly quite a lot. So if we only have 10 factors with 5 settings each, we have 5 to the 10 combinations. And this, if we want to test that, it might already be outside of what we can test. And combinatorial testing is the test approach that aims to solve that or help us at least dealing with the problem. Here we have a table, much more simple table with only 4 factors and 2 to 4 possible values for these factors. For a car that might have a radio, different engine tunings, a passenger airbag, yes or no, and possible sizes of displacements. What we usually then do is not to try to test all possible combinations of all of these values, but reduce it to a two-way covering array. So we want to have look at 2 factors and see if all combinations of these 2 factors are included in the tests. This 2 is a value for t, and t is the coverage strength. So if we increase that, we have a stronger coverage, but we increase, of course, the number of needed test cases very quickly. Other things that can help us is additional constraints that we can employ. So maybe an engine tuning might only be available if you have a certain displacement, or need more higher displacement to have be able to go for the big engine tunings, stuff like that. And this reduces, of course, the things that we need to test. There's tooling. This is the web-based tool Hexawise that allows us to specify inputs and generate then minimal test suites for a specified T coverage. Here in the example, it's Expedia flight reservations with 40 inputs. If you have reserved a flight in Expedia or a similar system, you know there's a lot of things you can choose and configure, and for 40 inputs it only needs 44 tests to achieve a two-way interaction between these things in these various aspects. Should a hotel be included, how many adults, how many seniors, how many children, and so on. So let us look at some questions. What is the main reason that most often T is smaller than 6 in T-way covering? And the answer is the majority of factor-related failures are caused by the interaction of a small number of factors. That's why even 2-way is often very effective. But definitely below 6 is usually something that is enough, because it's very rare that we have faults in problems that involve more than 5 different parameter settings. It will be a very complex fault and might not be worth the effort. Variable strength covering arrays. Use higher strengths for factors that are more likely to contain failures. So we can use the strengths not as one fixed value, but we can change it depending on where we think problematic or important or fault-prone areas are. You're building a completely new system and you have no idea what strength is suitable. You use incrementally covering arrays. As always, when we're not sure what's going on, we use iterations and increments. Same here. So you start with a rather low strength, and then as a seed, and then we build it up and use in each increment higher strengths until we have a good feeling that we covered the space well. Test runs are very expensive in the system you build. What fault characterization approach do you prefer? And the answer is probabilistic. Because probabilistic approaches use existing runs to make an uncertain diagnosis. And so we can reuse effort and be a bit uncertain in the beginning, but still are rather cheap. And then we use accurate approaches to run additional steps and come closer to actual faults. And there is no random approach in combinatorial testing. Now to the current research example, DeepCT, combinatorial testing for deep learning networks. In DeepCT, what interactions are subject to combinatorial testing? And in DeepCT, they use neurons in a layer. They claim that this is something that is not well covered by other approaches. In principle, you could, of course, apply combinatorial testing over layers, neurons across layers, whatever you want to look at. But they claim that this is a good focus. In DeepCT, what is the considered configuration? And they use as configuration the neuron activation. So 1, 0 for each neuron is what they look at, and they want to have a coverage of combinations of activations between neurons in a specific layer. And finally, an example: given the neuron activation status of neurons n, given test inputs t, what is the two-way combination sparse coverage? A measure introduced in the paper. So we have these 4 neurons, 1, 2, 3, 4. These are the columns, and in each row we have different activations done by the test inputs t, and we want to understand how well we already cover these neurons. And the answer is 50%. So out of the 6 two-way combinations of neurons that we have, we only cover fully 3 and 1 and 2 and 2 and 3 and 2 and 4, where we have the whole combinations 0, 0, 1, 1, 1, 0, 0, 1, and the other 3 not, and so we have 3 out of 6, 50%. And this ends the video. If you have further questions on combinatorial testing and each of the papers, please add them here in the interactive video or in the corresponding discussion forum.